Question number 1. Ammonium chloride decomposes into ammonia and hydrogen chloride. The question is how many components, phases, and degree of freedom are present in the system. So this is about phase rule. The phase rule says that the number of degree of freedom should equals to the number of components minus the number of phases plus 2. Note that the number of components is the chemically independent constituents. So let's look at the system. You have ammonium chloride, ammonia, and hydrogen chloride. So you have three constituents. These three constituents are not independent. They are related by one reaction, and therefore you have equilibrium constant. Okay, equilibrium constant relates three constituents. There's also a relation between these two. These two are 1-to-1 ratio, and therefore three constituents are related by two mathematical equations. One is Kp, one is the ratio, 1-to-1 ratio, and therefore you only have you have 1. So that is 3 minus 2 equals 1. Okay, three constituents, two equations, and therefore one number of components. So C is 1. All right. How many phases? You have solid. Okay, here is a solid. You have a gas phase, also gas phase. So gas phase is one phase. Solid phase, gas phase. So that's 2 minus 2 plus 2, and that gives you 1. So degree of freedom is 1. For example, this degree of freedom can be temperature. So if temperature is given, then according to Kp can be calculated. Okay, at a certain temperature there is a Kp, and therefore the pressure of these two can all be calculated with Kp. All right. If you change the temperature, everything changes. The pressure can be calculated. You only need 1 degree of freedom. So that's A. So in B, now suppose you add additional amount of ammonia. So if you add additional amount of ammonia, that means now ammonia and hydrogen chloride are not in 1-to-1 ratio. If you know one, you don't know the other one. They are not related. Okay, and so, but you still have this Kp, one equation. So you have 3 constituents, 1 reaction equilibrium constant equation. So 3 minus 1 is 2. So now C should be 3 minus 2. 3 minus 1. Okay, 1 equation, that's Kp. So that's 2. Okay, so 2 minus the phase is still 2 plus 2, and that gives you 2. Degree of freedom should be 2. Okay. Question 2. A saturated solution of sodium sulfate with excess amount of solid is present at equilibrium with its vapor in a closed vessel. Okay, so here is a closed vessel. Okay, with water and the sodium sulfate dissolved into it, and because it is saturated, there are some solids of sodium sulfate in it. So the question is how many phases and the components are present. Okay, so you have solid. This is the solid sodium sulfate. You have liquid. Okay, solid liquid, and also it says with equilibrium with the vapor, so you also have vapor phase. So pressure of water, so water vapor pressure, and therefore this is vapor phase. You have three phases. Okay, how many components? Components is the independent constituents. Here you have water, you have sodium sulfate, and there's no chemical reaction between them. There's no mathematical relation between them. So you have two constituents, that's two components, okay, in this system. So what is the degree of freedom? Okay, variance also means degree, number of degree of freedom. So according to phase rule, should be C plus 2 minus P. C is 2 minus 3 plus 2, that give you 1. Only 1 degree of freedom. Identify the independent variable. This independent variable can be temperature or can be pressure, but cannot be both because you only have 1 degree of freedom. So if you change temperature, then the vapor pressure can be calculated. Okay, so or if you know pressure, then the temperature can also be calculated. So only 1 degree of freedom. So in question number 3, you have a mixture, solution of AB. So let's draw. You have liquid, mole fraction of A is 0.6589. You also have XB, which is 1 minus XA. All right. So the boiling point of this solution is 88 degree. At 1 atmosphere, and at this temperature, the vapor pressure of pure A, okay, note it's pure A, is 957. So pure A vapor pressure is 957, okay, tall. Assuming it's ideal solution, calculate the vapor pressure of pure B. So it'll ask you to calculate the pure B vapor pressure. Okay, so if you have mole fraction in the solution phase, all right, we know that the pressure, okay, above it should obey Raoult's law. So the vapor pressure of A above the liquid should be the vapor pressure when it's pure times mole fraction. Okay, so you can calculate because this is already given here, and so you can calculate the vapor pressure of A above it. Okay, what about the vapor pressure of B? Okay, it's the vapor pressure of B when it's pure times mole fraction of B. So this is not given. Okay, it asks you to calculate vapor pressure of B when it's pure. Okay, what is also given is that the boiling point at 88 is under pressure 1 atmosphere. So it means that actually the total pressure inside here is 1 atmosphere. Okay, so PA, vapor pressure of A, can be calculated according to Raoult's law, and total pressure is given, and therefore you can calculate the vapor pressure of B above the solution. Okay, and then use Raoult's law, you can calculate the vapor pressure of B when it's pure. Okay, because mole fraction is given. So if you can calculate the pressure, you can calculate the pure B vapor pressure. All right, so use Raoult's law. First calculate the pressure of A above the solution. Okay, and then use total pressure minus, total pressure is 1 atmosphere, which is 760 torr, minus the vapor pressure of A, give you the vapor pressure of B. And then use Raoult's law again. Here in this equation, this is unknown and this is calculated, and so calculate vapor pressure of B when it's pure can be calculated. Okay, so that's question A. So in question B, what is the initial composition in the vapor phase? In other words, what is YA, YB in the vapor phase? And we have seen this kind of question again already, and that's use Dalton's law. In the vapor phase, the composition mole fraction equals partial pressure divided by total pressure. Okay, so total pressure. So total pressure is 1 atmosphere, 760 torr. Partial pressure you already calculated here. Okay, that's the vapor pressure of A. And similarly, this is the vapor pressure of B. You can calculate the mole fraction of B. Okay, it asks you why it says initial composition. Okay, why it says initial composition? The reason is that with time, more liquid goes to the gas phase and the composition will change. And this is only at the beginning. You know the mole fraction in the solution, and therefore you can calculate the vapor pressure in the gas phase. Question number 4 shows two phase diagrams for a mixture of hexane and heptane. One is for pressure composition, one is for temperature composition. It asks you to label the regions of the diagram as to which phases are present. As we mentioned in class, these two phase diagrams are similar, but there are differences. For example, at high temperature, liquid is the most stable phase. But in the second phase diagram, liquid is at the low temperature. Low temperature favors liquid phase. When you increase temperature to high temperature, it's the gas phase. So gas phase at a high temperature, but on the first diagram, it's the low pressure is the vapor phase. They are opposite locations. In between, there's two phases, okay, liquid and the vapor phase. Okay, so that's A. In B, for a solution containing one mole each hexane and heptane, that means the mole fraction for both are 0.5. Okay, it asks you to estimate vapor pressure at 70 degree when the vaporization on reduction of external pressure just begin. So this is about the pressure reduction and the liquid start to boil. Okay, so we should use the first diagram. All right, at 70 degree when you reduce the pressure. Okay, so where is the initial point? The initial point is any point here. Okay, that will be mole fraction 0.5, and it's a liquid. When you reduce the pressure, it goes down until it touches this line. It starts to vaporize. Okay, to find the vapor phase, we draw the teal line. Okay, so here is the vapor phase, here is the liquid phase, and the pressure here is 620 torr. Okay, that's the pressure when the liquid starts to boil. Okay, the next question is estimate the mole fraction of heptane in the liquid and the vapor phase. Okay, so liquid phase is here. Okay, is 0.5. Okay, you just start to boil, so the mole fraction is the same as the initial mole fraction, and the gas phase is 0.28. Next question, at 80 degree and the 760 torr, what are the amount substance? So now we have to use this one. Okay, 80 degree. Okay, the first diagram is about 70 degree, and so 80 degree is here, and the pressure is here. All right, so temperature, you go draw teal line, and the mole fraction initially is right here. Okay, and so initial point should inside the two phase region, and therefore it separates into two phases. It asks you how many goes to the gas phase. Okay, N, L, and V. What is NL? What is NV? And now we have to use level rule. So let's go to the next slide. Okay, so in this slide, we have two phase region, initially 80 degree. Okay, so the point is here. Okay, it asks you what is NL, what is NV. Okay, the level rule says NL times LL should be NV times LV. So modify this equation. NV divided by NL should be LL divided by LV. LV can be measured in this diagram. You can see LL is slightly longer. It's actually longer than LV. It's twice that. And therefore, NV divided by NL is 2/1. All right, to find out exactly what is NV, we need one more equation, and that is the total number of moles is 2 moles. How do you know that? It says you add 1 mole each, and therefore the total is 2 moles. Okay, so combine these two equations, you can solve NV. Okay, so one way to do it is that this equation says NV should equals to twice NL. Okay, so plug in this equation. So you have 2NL, that's NV, plus NL equals 2. And therefore, NL should be 2 divided by 3. All right, and therefore, 2 divided by 3 is 0.67 moles. And for NV, you can just use 2 minus 2/3. That gives you 1.33 moles. In question number 5, based on the phase diagram below, which one is more volatile, A or B? Okay, so in this phase diagram, one boiling point is 80, one is 50. Okay, the mole fraction is about A. So at the right side is pure A. And pure A boiling point is 50, and pure B boiling point is 80. And therefore, the more volatile compound is A. Okay, next question. A concentrate solution of B is distilled in order to get pure A. What is YA in the vapor phase? So this phase diagram is about mole fraction of A, and the given is about B. B is 0.9. You need to calculate A. So XA should equals to 1 minus XB. That's 0.1. And so the phase diagram should be somewhere point here. Any point here, all right, is a liquid with mole fraction 0.1 A and is a liquid. Okay, when you heat it, temperature goes up until touch this line, it starts to boil. The question is, what is YA in the vapor phase? So you draw teal line, and the vapor phase is 0.42. You can see that in the gas phase you have more A in it because A is more volatile. Okay. Now the question C, in order to get 0.9 A in the gas phase, how many theoretical plates you need? All right. So one theoretical plate is not enough. You only get 0.42. That's one theoretical plate. You need the second one. Okay, so you let the vapor phase becomes liquid and vaporize again, and now you get about 0.885 somewhere, and that's still not enough. So you need another one. Okay, and now with the third one, the mole fraction is about 0.95. And that is more than necessary. So theoretical plates should be 3. Question number 6. What factors determine the number of theoretical plates required to achieve a desired degree of separation in fractional distillation? The most important factor is the the shape of the phase diagram. As we mentioned in class, the shape of the two-phase liquid vapor region in the phase diagram affect the separation. The closer the liquid and vapor line are to each other, the more theoretical place you need. In addition, the azeotrope also have important consequence on the separation. The presence of the azeotrope will prevent the desired degree of separation from being achieved.